Good morning everyone. I am Renu Sharma, Assistant Professor EC Department from Ajay Kumar Kark Engineering College. Today I am going to continue the next part of Unit 1st for the subject, that is wireless and mobile communication. Its code is KEC076. So the contents of today's lecture are: first we will discuss AWGN channel. Now when we are talking about wireless communication, then in case of channel we have to consider a model which is whose PDF, or we can say the probability density function, is calculated, means it is fixed from -infinity to infinity. For AWGN, its PDF is fixed, that is n0/2. So additive wide Gaussian noise is the full form of AWGN channel. We will discuss in detail. Then we will discuss this Rayleigh fading model and channel impulse response. So these are the topics. So we will start with AWGN channel model. So the received time domain signal, that is denoted by Rn. Now why we consider Rn? Because since it is a discrete time signal, then we have considered this Rn. It is a function of the transmitted signal, that is Sn, and the estimated channel transfer function and the AWGN noise. So basically, if I am going to draw a model for this received signal, then the signal will be like this one. Like this will be the input signal, then this will be added with this noise, that is additive wide Gaussian noise, and at the output we will have this received signal. So after traveling over a channel where it will be interrupted with noise, which is additive wide Gaussian noise, and with the addition of this one we will have this Rn signal, that is nothing, this is the received signal. So this equation can also be written as Rn is equals to Sn convolution with, this is a convolution sign with HEN. Now HEN is nothing, it is the estimated channel impulse response, because whenever we are going to draw we are going to design or any channel is designed, then it is based on some function, like it may be a Rayleigh function, it may be a Rician function, which has their own probability density function on which that particular channel is designed. So for that we will consider a impulse response that is denoted by HEN. This is the estimated one, because when in real time application, this signal the channel will be affected with many noises which will going to change the characteristics of the signal which through which it will be traveling. So that is HEN, which is the estimated channel impulse response. The whole time domain scenario can be mapped into the frequency domain representation. So when we want to process any system, maybe it's a transmitter, receiver, or a channel, then we have to consider, or we have to convert the time domain signal into frequency domain signal to visualize the frequency spectrum of the frequency domain representation of the particular function from which the maximum information can be extracted. Now next one is the stochastic radio channel modeling. In principle, the following three different domains determine the radio signal transmission. So basically there are three different domains are there. Now first one is the operation scenario, implies some fundamental data such as frequency range, system bandwidth, environments, like it may be a rural environment, urban, or indoor. So basically in the first point what it is discussed, that whenever a channel is designed, then we have to consider, or in other way, if I am talking about when we divide a particular geographical area into different cells. Now these cells, the size of that particular cell or the radius of the particular hexagon is decided by the population which it will going to cover. Let's say large population area has to be covered, then the cell size will be very small, because it will reduce the probability of handoff. Now next one is when the population size is quite large, then a larger size, smaller size areas will be considered. So vice versa we have to consider. Next one is whether it is used for outdoor application, whether it is used for indoor application. So all these parameters keep into mind for designing a particular channel. Next one is dispersion in frequency, time, direction and polarization is a crucial aspect of radio communication. So, this is related to the antenna, in which direction it has to be, it has to face, like whether I can consider a omnidirectional antenna, I can consider a directive antenna which will going to direct the energy in a particular direction only. So, based on that, dispersion in frequency or time is there. Now, what is dispersion? Dispersion is basically spreading of the pulse whenever it will going to travel over a longer distance. Let's say I have transmitted this square wave that has a duration from 0 to t, its amplitude we can consider any amplitude, that is A. Now, after traveling over a channel, this is a channel, it will going to disperse due to the effect of noise. So, you can see that this part has been dispersed. So, this will be 0 to t plus tau and its amplitude will be is equals to A. Again, it can be increased, it can be reduced, because noise can be constructive or destructive in nature. So, but you have to see this, that the time duration has increased from t to t plus tau. So, that is known as dispersion in frequency. Now, the transceiver is made up of two things, that is transmitter and receiver. Characteristics contributing to the stochastic radio channel modeling, that is SRCM, are the parameters that describe the empty movement and the antenna configuration with its radiation pattern and delivery diversity property. So, basically in this what we have to consider, that the transceiver characteristics, like for the transmitter and receiver, since both are mobile in nature, means both are moving in nature. So, we have to consider the radiation pattern and the diversity properties of the antenna, because we are talking about the wireless channel modeling. So, we have to consider that first thing, there is no direct line of sight is there, there is no connected communication link has been set up between the transmitter and receiver, all the things are broadcasted in nature. So, definitely there will be multipath propagation is there, which will in which scattering, diffraction, reflection, all these four parameters will be considered, will be counted for the purpose of transmission. Now, next is space alternating generalized expectation maximization, that is SAGE algorithm. So, the full form of SAGE is this one. Now, this is the SAGE algorithm which will going to design a channel model. Now, you can see over here that this is the RF input. Now, RF input is nothing, it is a signal which is being present in the radio frequency range. So, this is RF frequency range. Then it is passed through an ADC, that is an analog to digital converter. The three operations which are carried in this ADC are, first one is sampling, then there will be a quantization, now the third operation which it will going to consider is encoding. So, after this, after the three stages, you can say, or the three steps, the analog signal is converted into digital signal which can be shown in terms of zeros and one. Now, after that, it will be passed through an add fading, that is a Rayleigh region log normal model. It can be a Rayleigh model, it can be region, it can be log normal. So, they basically three different types of fading models are there. Next one, at the receiver side, it will be a DAC, that is a digital to analog converter, because the original signal is in the form of analog only. Then we have to add a AWGN noise, that is additive wide quotient noise, and the output will be the RF output. So, you can see over here that the input is RF, output is RF, and in between that we have added fading, we have added AWGN to see the channel modeling. Now, this is the process must be repeated for any change in the power. So, whenever the power will going to change, means the input will going to change, these three steps has to be followed, like measure the output power, add noise, and measure the total power. So, at an average we have to consider this. So, this is a basic model of SAGE algorithm that will going to design, that can be considered for the designing of a channel. Next one is Rayleigh fading model. Now this Rayleigh fading model is very famous. It has its own PDF, it has its own probability density function. Now you can see over here, like the first diagram is the sample of a Rayleigh fading signal. These are the samples which we have extracted from the original signal. Now you can see over here, this is a graph which has been drawn between the signal amplitude versus time. This is a threshold which has been set, and this is a non-fading duration. These two are, and these are the fading duration. Now you can clearly visualize from this graph is that whenever the fading is there, then the amplitude will be below threshold, and when there is no fading, then the amplitude crosses the threshold. So you can see that whatever signal which we have received, we have to set a threshold level, and then when the signal which we have received crosses the threshold, we can see say that it has no fading. No fading has affected that particular signal, and if it is below the threshold, then we can say that the fading is there. So this is how we have to analyze the received waveform depending on the distribution or depending on the function which we have considered for designing the particular channel. This is a Rayleigh PDF. This is a very common Rayleigh PDF that is having probability density function. This graph has been drawn between P alpha to alpha. Alpha is the parameter. Its value can be 0, 1 and 2, and you can see over here that at 1 its value is maximum, and this is a normal. You can say at value 1 it will act as a ideal filter. So that is a Rayleigh channel model. Now C is showing the variation in the Rayleigh. Now you can see that depending on the values of sigma, like for 1 its value is, its representation is shown over here. For 0.5 its representation is shown, and when we are going to increase its value, like sigma is extended to 4, then it can be extended to 5 also, then you can see that this graph or the slope will be towards this origin only. So this is how this is showing the variations in the Rayleigh. Now next one is the variations in the Rayleigh CDF with change in standard deviation. That is standard deviation is being shown over here. This is CDF. Now you can easily see that PDF is the differentiation of CDF. So if we know PDF, we can calculate CDF, and vice versa. If we know CDF, we can calculate PDF also. CDF is integral of PDF. So this is, you can see over here in CDF that as this 0.5 sigma is going to decrease, or you can say it is increase, it is going towards this origin only. So this is the representation of PDF and CDF for Rayleigh model. Next one is the multiple Rayleigh fading channel. Now this is showing the two extreme cases are distinguished, like first one is the coherent accumulation, second one is incoherent addition. So first I'll discuss what is coherent and what is incoherent. Coherent, if we say in simple layman language that what is coherent, whenever we are talking about modulation, then for modulation we require two types of signal. First signal is the message signal, second one is the carrier signal. Now the same in case of analog modulation, the carrier signal is continuous in nature, so the same carrier signal has to be used at the receiver side so that the coherent detection will take place. If the coherent detection will not take place, so it is possible that the signal will be received with a delay, or some it will not be received. In the same way, if we are talking about digital communication, in that situation, that signal which is being used for modulation will be in terms of 1 and 0, so that should be used same as at the receiver side to maintain the synchronization. So that is coherent detection. Incoherent is just opposite of it, that in case of analog it should not have the same phase and frequency as that which is received at the, which is used at the transmitter side. So coherent cumulation is also known as the phasor cumulation. It occurs if during the observation interval the fluctuation of the phases caused by the modulating signals are sufficiently small and the carrier frequencies of the signal are exactly equal. So basically in case of coherent, what I was talking about, if it is having the same phase and frequency, that's what it is written over here, that the carrier frequency of the signal should be exactly equal. The joint signal behaves as a Rayleigh phasor with the Gaussian in phase and quadrature phase components. The instantaneous power is exponentially distributed. The local mean power is equal to the sum of the local mean powers of the individual signal. Now you can see over here, this is a graph which is been drawn between quadrature phase and in phase component. So these are the two components, what are quadrature and what are in phase components. Let's say I am talking about QPSK. QPSK is a kind of modulation technique, that is quadrature phase shift key. Its block diagram is somewhat like this. This is the input signal. I am drawing the transmitter side. This is the input signal which is continuous in nature. Then we require a carrier signal. A carrier signal can be a cosine or sine. Then it is given directly to this one, and this has been passed through pi by 2. So a 90-degree phase shift we have to apply. We have to provide to this carrier signal. Then the output will be summed up. So this component, this signal is being transmitted over the channel. So the basic concept of in phase and quadrature phase is that whenever we are going to use the same carrier frequency which is being generated from the local oscillator, then that is known as in phase component, and when we are providing 90-degree phase shift to the carrier signal, then that is known as quadrature phase component. So this is the quadrature phase component. So this is in phase and quadrature phase component, and this is how we have to consider the two components. Now you can see over here that this is the quadrature phase versus in phase component which is drawn over here. Now you can see that this is the resultant wave and this is the reflected wave. So whenever the in case of multipath propagation, whenever the wave is reflected, then its power will be reduced, or you can see that the loss of energy will take place. In case of reflection, refraction, diffraction and scattering, definitely the same strength of signal you cannot receive at the receiver side. So the local mean power is equal to the sum of the local mean powers of the individual signal. So whatever we have received from multipath propagation, it has to be summed up before it will be at the receiver side. This is the probability density function of the Rayleigh function. Now you can see that this is the gamma distribution for the arbitrary variable, that is x. Now this is a graph which is being drawn between fx versus stochastic variable x. This is a kind of random variable only, and you can see that its value will be increased in this interval, and its variable is shown over here. This is Nakagami distribution. In my previous lecture I have discussed about different path loss model. One of the model is Nakagami model. In case of this Nakagami model, you can see over here, this is a PDF which is being drawn. PDF alpha is drawn versus alpha, and its value will be varying from m is equals to 1, 1.5, 2 and 0.5. So this is all with the variable m. So with the changing value of the m, the slope of the particular distribution function, in case of this Nakagami, it will going to change. Then this is varying from 0 to 0.5, and you can see that for m is equals to 0.5, it will be extended towards it will be kind of a linear function. So this is a Nakagami distribution. Now next is the block diagram of a narrowband Rayleigh fading simulator in the baseband form. Now in baseband form, what does it mean? That we are not using any kind of modulator or demodulator. In case of passband, we have to use a modulator and demodulator. So this is the signal input. It will be an RF input, that is a radio frequency input, which is provided to this quadrature hybrid system, then to this there is product modulators which are used, and we are using white noise which is given as an input to this system and which is given input to this system. So the summation has been considered, and after adding the various values of the white noise, it will be given as an output. So this is the signal output which has been summed up together. So this is a block diagram of the Rayleigh fading distribution, means it is based on the Rayleigh distribution which we have seen in the previous slide. And this is a quadrature hybrid. You can see that there are different delta, which means these are the weighting function, these are the weights, or the multiplying factors are there. These are the weights and these are the different values. So these are summed up together and these are provided to the output of this will be provided as a product modulator and then summed up together. So this is the basic model. Next one is simulating Doppler effect. Now, what is Doppler effect? If we talk about Doppler effect is basically means whenever we are considering any radar or a system, when the system is moving away from the target or it is moving away towards the target, then the change in the frequency will take place. Either it will be added or it will be subtracted. So it is a common practice to generate two filtered noise components by adding a set of 6 or more sinusoidal signals. So basically you can see over here that different signals will be added together. So their frequencies are chosen to approximate the typical U-shaped Doppler spectrum. You can see that if we are considering 6 or more sinusoidal signals, then the shape of the Doppler spectrum will be like this one. This is a U-shape kind of spectrum. This is extended from Fc minus Fd to Fc plus Fd. Fc is the carrier frequency and Fd is the Doppler frequency. So sometimes it will be subtracted and sometimes it will be added. And the end frequency components are can be calculated from this formula only. Next one is the Rician fading model. So likewise, the Rayleigh fading model, the Rician channel model is there. It is similar to the Rayleigh fading model, except that in Rician fading, a strong dominant component is present. This dominant component can, or for instance, be the line of sight wave. The refined Rician models also considered with the following point. So basically there is a relation between or you can say the similarity is there between the Rician fading and the Rayleigh fading model, but there is a strong dominant component which is present in the Rician channel, and that may be a line of sight wave. So with these two points we can consider the updated version of the Rician model. These are the diagrams which is shown for the Rician fading model. This is Rician PDF which is being shown over here. This is B. This is, and the parameter you can see that this is A by sigma, and when its value is 0, then this will be an ideal one. Its maximum energy is concentrated over the origin only. Next one is the Rician CDF with the change in standard deviation. So this is the diagram which is shown over here. So in this lecture we have discussed about the channel modeling, which is discussed about Rayleigh model channeling and Rician channel modeling. So this is all about today's lecture. Thank you.